So I'm going to talk about selected CI or selected configuration interaction trial wave function with quantum packaging against back. So basically, it's still the same source of funding as yesterday, so I can continue on this. So basically, the motivation why we need selected CI, or what's the point of using multi-reference trial wave function, comes from the fact that in the past years we have seen many calculations using single determinants of Monte Carlo. These gave pretty good results in the literature. A lot of people are very satisfied. For the solids, we can reach very high accuracy. Also for molecules, for closed shell, we're pretty happy about it. However, the accuracy, if we want to be very realistic, is about a few kilocal per mole to 0.1 electron volt, which is slightly high number of kilocal per mole. The reason for that is when you get below chemical accuracy, mainly it's luck because your normal surface was pretty good with the wave function that you have tried, but this is not a generality. It's basically system dependent, and we get more or less stuck at trying to get those accuracies. So these sources of bias, why do we have, why can't we reach the ultimate accuracy that we want, can come from multiple biases or approximations. Some of them are pseudo-potentials. So like we have seen yesterday, like increasing the quality of your pseudo-potential will decrease significantly the error that you have, and sometimes even give you a better result, as we have seen, than using all electron calculations. There's the locality error that we have not talked too much about, but I think Miguel had mentioned it quickly yesterday. There are a lack of spin orbit. If you try to do gold, or if you try to do platinum or silver or these things, well, maybe not silver, but gold, we know that there is some spin orbit coupling, and we do not have a theory that includes spin orbit coupling. So this will generate sources of errors. All those, however, are controllable in the sense that we will be able to get great pseudo-potentials like we have seen. We can completely remove the locality error. We can add spin orbit coupling. These are controlled biases. However, the only one that we do not control is the fixed node. No one knows what is the fixed node supposed to be. No one knows the quality of your fixed node until you try. And so that's the really source of error that we have. So we know, however, that DMC is variational. So we know that if you change your trial wave function, if it increases or if it improves your trial wave function, your nodal surface, your energy is going to be lower. So we can scan through multiple nodal surfaces to try to see which one is the best. And this is what has been done in the past. So this is the state-of-the-art way that we have to more or less try to improve our trial wave function, where, for example, for the solids, we can take an LDA plus U or a GA plus U. So this is the Hubbard view, where we artificially add some energy to the d electrons to try to promote them, and that is going to move them a little bit higher, and we can, like this, just improve our nodal surface. So this is what is done, for example, for transition metal oxides. This is here the case of the nickel oxide, and we can see by modifying the trial wave function, which is at the DFT level, we just move this U until we reach minimum. And in this case, we were lucky that either with LDA plus U or GGA plus U, so two completely different functionals, we reach the same minimum, but for two different values of U. Then we're happy. We think that we're optimized. In the case of molecular systems, this was done here by Lucas Wagner, where you just take a DFT and you start playing with the amount of exchange, exact exchange in a functional, until you get a minimum energy, and then you say, okay, so this percentage of mixing gives me the correct nodal surface because I have the minimum. But this is not systematic. And moreover, there is no guarantee that this is an absolute minimum. This is basically just minimum that we are finding here based on whatever modification in 2 dimensions that we have chosen. So that's great, but it's not systematic. These calculations were extremely expensive because this means that we had to do solid calculations instead of just 1 point. We had to do 10 points. So this is 10 times more expensive than it should have been. And again, we cannot even say with certainty we have the best nodal surface. We can just say we have the best in our opinion or as far as we tried. So that's not good enough. In quantum chemistry, this has been done in the past by Morales and I in 2012, so this is starting to be in all the papers. So they started by just adding complexity to the trial wave function. So we know that the nodal surface is not as good as it is because we just take the ground state. So we just put all the weight into the ground state. However, if we were to take a multi-determinants later JASTROW wave function, where we start adding more options or more possibility of determinants, we increase the quality of our nodal surface. And we can see here by just this here, the value here of the 0.015 is the coefficient or the weight of each determinant that we are adding. So if we start doing MCSCF or CASA-CF type of calculation, and we add determinants that have weight higher than 0.015, 0.75, 0.5, so we're increasing the number of determinants in our expansion, we see that we are reducing the energy or reducing the error that we are having compared to what it should be, and this is on the G1 test set. Same thing happens for the VNC. So we can start already seeing that we are reducing the error by adding the complexity of our trial wave function. So that's great. So there is a path forward to try to systematically improve the quality of our nodal surface. However, this paper here, it used a CASA-CF type of calculation. So we all know, or at least chemists know, that when you do a CAS, it becomes quite a challenge because you need to understand exactly each system individually and try to understand, okay, I'm going to add orbital 16 to 25, and I'm going to allow them to excite from singles and doubles. So basically, you need to be a specialist for each one of these methods. So in my opinion, that's not necessarily the most systematic way. And since I'm not a chemist, these methods are just forbidden to me because I don't know what I'm doing. So how's that? I cannot move up or down. I think so. Okay. Yes. Okay. So what is a better way, or at least what do we think could be a better way? Well, the ultimate way, or the ultimate trial wave function, or the most accurate calculation you can do in quantum chemistry is still a full CI calculation, full configuration interaction, where you basically take a variation wave function that is a linear combination of all the configuration states built from spin orbitals. So basically, you take every possible excitation you have from every electrons that you have. So let's say this is your ground state. So basically, it means that you're going to take a linear combination of all the single excitations, all the double excitations, all the triple excitations, and you continue like this, so on and so on, until you have a linear combination of all of them. And this is the full CI, full configuration interaction. And of course, this scales with this is factorial scaling. So obviously, you're going to go not very far, and your space, your Hilbert space, is going to have, like for a small system, you can end up with 10 to the power of 19 determinants that you have to add into your space. That's insane, and it's going to take you cannot do more than, I think the best people can do maybe 5 electrons, and they are super happy when they can do that. And so that's great, but that's not useful at all. So we know that we are adding here this linear combination of all the determinants. We know that the most important one usually is the ground state. Most of the way
the single determinant,
yes.
Right, the HARTREE-FOCK determinant.
The HARTREE-FOCK determinant is usually, okay, when you are sure that your HARTREE-FOCK converges to the correct ground state, then you can be sure that that's going to have most of the weight, unless it's a very, very weird system that you know of. Probably you're going to have, like at worst, you're going to have a 0.6 or 0.7 weight on your ground state. And the rest is going to be split over maybe the first 1,000 determinants are going to matter. And the rest you're just having garbage tail. And I'm going to come to that garbage tail towards the end. So, of course, in our case, if you want to have 18 digits after like accuracy, you will need all of them to be able to account for this. But most of us, we are happy with the kilocalorie per mole accuracy or sub-kilocalorie per mole accuracy. So the idea behind selected CI is that basically it would be great to only select or only pick the determinants that are going to contribute the most to our energy and throw the others. Why bother computing all the 19th or the 27th excitations if it adds to the 10 to the minus 25 to the energy? we don't care about that. We can make that approximation. It's fine. And remember, we do QMC, so anyways, we have an error bar at the end. So why should I care about those? So this idea was actually found in there's a paper before this one in 68, I think was 63. And it's a method in the idea that you can use selected CI or just put some criteria that you're going to use to select determinants one after the other instead of picking all of them. And this was thought of in the 60s, then forgotten, then thought again in the 70s, then forgotten, then in the 80s, forgotten. And like this, every 10 years, someone rewrites the paper and forgets about it until 2009, I think, or 10 in France, where Michel Caffarel thought about it again, made a presentation in his lab. The problem for him is that he was sharing his lab with this guy. And he was very proud to tell everyone. So I found this fantastic idea, and I wrote the code, and you had this old guy there and say, well, I wrote a paper about it in 78. So it was a little bit funny. And they started collaborating again. And this is where they wrote, so this is called selected CI, and their version or their way that they do it is iterative perturbation calculation. It's selected configuration interaction perturbatively and iteratively selected. So it's a horrible name, but it's CIPSI for CI, psi for configuration interaction wave function. How does it work? So it's relatively simple. So we start from the ground state, which is HARTREE FOCK. So we have one determinant of HARTREE FOCK. This is step one. Now we're just going to generate from this HARTREE FOCK all the single and double excitations possible. So we're just going to build all these determinants. Now we have a set of all singles and doubles. We are not computing them. We just generate them. So we just generate them. We do not know the contribution of each determinant. Now we're going to evaluate from the second order quantification, the second order perturbative contribution of each determinant. So we're just going to get the energy from the second quantification of each determinant individually. And we're going to see if this contribution is larger than a threshold that we set in the system. So let's say I want my determinants to contribute maximum or minimum to 10 to the minus 4 to my energy. If this determinant does not contribute above this threshold, I do not add these determinants to my Hamiltonian. If it does contribute, then I will add it. So now that I have all the determinants, so I eliminated all the crappy determinants that I don't care from the first and second excitations that I have, I enter them in my trial wave function, and I updated the Hamiltonian. So I rediagonalize again, and now I have a new Hamiltonian containing only this new set of single and double excitations that matter the most. And I do it again. So now I am here at this point. I have entered X number, 8 maybe, I don't know. I enter them. And I repeat the operation of doing single and double excitation on the previously single and doubled determinants. So now I'm going to have doubles and triples. And I redo the operation. So now I increase again the set of determinants that I have access to. I redo the operation of evaluating the energies. If it's below the threshold, I remove. If it's above, I keep. And I repeat the operation over and over, and I start adding. So first I add single and doubles, then I excite them, then I'm going to have doubles and triples, triples and quadruples, quadruples and sextuples. So I do not limit myself only to singles, doubles, triples. I just take all of them, as long as they matter, as long as they contribute to the energies, I just keep adding them. And I start just adding them slowly, 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 until I reach this convergence here. So this is an FCI, so I start from HARTREE FOCK, and this is an approximation to the full CI limit. So rigorously and mathematically, if I put my threshold to 0, which means I take everything, it's mathematically the full CI solution. There is no other approximation here, except the fact that I'm entering them one after the other iteratively. So,
what do you mean adding to the Hamiltonian?
Sorry?
What do you mean by adding?
So you have one, so you just have your wave function that has one determinant. So now you have your wave function that has linear combination of, let's say you selected in your first trial 5 determinants. So now you have linear combination, your wave function has 5 determinants in it, and you just need to rediagonalize the Hamiltonian with this new wave function. So you just apply it to psi h psi. So you just enter them again in your wave function. So you have a wave function that you start with a wave function that is single determinant. At the second round, you have 8 or 10 determinants. So So you need to rediagonalize your Hamiltonian to have new eigenvectors, new eigenvalues, and you repeat the operation.
It's like doing the Hartree FOCK with the new wave function.
It's not Hartree FOCK anymore, it's CIPSI.
Restricted CI.
It's a restricted CI, yeah. So you're just having more, so it's at step one, you have one determinant in your Hamiltonian. Now you have, in your wave function, now you have 10 determinants, and you just keep increasing the size, but you still need every time to diagonalize your Hamiltonian to have new eigenvalues and new eigenvectors and new coefficients for your Hamiltonian. So, okay, so basically you start here and you start just increasing the number of determinants. So there are interesting things here to see. So this example, of course, works for, I'm going to get back to it. Okay. So the good part about this is that this is a systematic improvement of your wave function. This is not a case where you add some determinants and it gives you spikes and then, or it increases the energy. The more you add, the lower your energy is going to go. So there is no, it's a systematic improvement. The more you add determinants, the better you're going to be compared to your first point here. There is no situation where you're going to find something going up. So the hope when they did this was that the nodal surface at the QMC level will follow the same improvement, systematic improvement. So, okay, so I have this thing here, but you can see that it takes time for it to converge. This is about 1 million determinants. Knowing that, so this here system is a carbon solid, and it works for molecules and for solids, but I will come back, I just use the solids as an example here because I had prettier pictures for the solid. But this space here has about 10 to the power 36, if I remember well, determinants. So 10 to the power 36 is your result for the full CI energy. I get the same result here with about 1 million determinants. Sorry, I'm spoiling. Don't look. Okay.
We go back.
I got it. Thanks, sorry. So you see between 10 to the power 30 to 10 to the power 6, that's a big improvement. And knowing that this calculation run on my laptop in about 2 hours. Okay. Now, another thing that is interesting when we do this evaluation of the second order perturbation energy is that at all times, the evaluation of this PT2 energy or this error that we're introducing, when you do the sum of all these determinants that you have, this is the PT2 energy. This PT2 energy basically estimates the distance to the exact full CI energy. So every time you do one calculation of this PT2, it reduces, it goes down. So this energy, when it reaches 0, that means that you're introducing a 0 error between your full CI estimate and the value that you're computing. So if you plot this PT2 energy plus the energy with the number of determinants, it's the curve that you see here. And this curve actually converges faster. Basically, it means that at every time when we do this evaluation of the second order perturbation energy, we have an idea of the error that we're introducing. So at the beginning, this error that we are evaluating, that we think we are introducing, is very large. But the moment we start adding more determinants, we start just having a better grasp on the determinants that are left. So we have an idea on how much energy we are adding. So after a while, this here converges way faster. So we know, for example, if we did not care about the QMC energy behind it, we could just stop here at 2,100 determinants when the energy plus PT2 stops moving. So we know that all the rest here is going to be, we don't need it if the thing that you want is really just the energy. So there are ways to be able to estimate how far you are from the full CI energy. And of course here, this is pretty fast. This takes about a few minutes to get on a laptop. Okay, so what does it do if I use this now nodes with this multi-determinant expansion in the QMC level? And remember, this is for a solid. This is for the carbon solid. Even if Miguel said carbon is easy, that was not that easy to reach this point. So here I have the nodes for carbon solid. This is just a single cell, so I'm not going to go that much into details in here, but this is using the LDA, PB, and BQLIP nodes. This is Hartree FOCK node. And now these are the nodes using 8 determinants, 226, 2,000, 160,000, and 1.2 million determinants. So first of all, we see that we are able to systematically and smoothly improve the quality of our DMC energy. And this smoothness here follows exactly the same one as we have for the selected CI calculation. Here also, we are introducing quite, I mean, this is a 30 milli HARTREE or 40 milli HARTREE improvements on the quality of the nodal surface. So remember, DMC is variational. Any nodal surface that gives you a lower energy is a proof that your nodal surface is better. So we are able to get this. The other good thing is that around 2,000 determinants here, we are also already converged more or less at 3 milli HARTREE from the fully converged full CI calculation or selected CI calculation. If you remember from the slide that I showed, if you remember from this slide here, this 2,000 number is more or less the same point where we have a convergence of the energy with PT2. So basically, this PT2 here also tells us that at the same level, probably your nodal surface is getting the same quality accuracy that you need to be able to complete it with the at the DMC level. And this is something that is quite nice because we know more or less what is the threshold that we need to converge. So, okay. The second thing is that, so what are these multi-determinants? So why do we have all these determinants at the end? Why did I need 1.2 million determinants when actually my DMC could converge at 2,000? So what happens with that 1-point-something million determinant that I'm having? Well, that's quite simple when you think about it. It took me time to understand it, but basically, the electron-electron cusp. So in quantum chemistry methods, this is here for, I think, a helium system where we have 2 electrons. And we just rotate them. So they are, when they are completely far away from each other here, and at 0, they are on top of each other. And we need to compute the cusp. So this is the interaction, how much correlation you have when you have 2 electrons on top of each other. So we see that HARTREE FOCK basically has no correlation and takes absolutely zero cusp. This one here, the lowest one, is the full CI limit. So we see that at 0 here, all the contributions of the multi-determinants is just, so this is the full CI, and now it's the number of determinants that we have. So the more we increase the number of determinants, the closer we get to the shape of the correlations here near the cusp when you have 0. So basically, all the determinants that you have, what they do is that they correct for the cusp. When you are far away, they more or less all get closer to the full CI limit. So we can describe correctly at large distances. When it starts to become funky is really just at this point here. So when you have the cusp, at the cusp region. So basically all your determinants, this tail, this garbage, these high order energy coefficients that you're adding for your determinants, all they do is just correct for the cusp.
So why is your full CI curve not look exactly?
Which one?
Your full CI curve.
I
mean, it looks smooth.
Finite basis.
It's just a finite basis. So
yeah.
It can't have it.
So basically, only thing that we are doing is correcting this. But at the QMC level, remember, we use JASTROW functions. And especially, we use a two-body JASTROW function that takes into account the electron-electron interaction. This electron-electron interaction, what it does, we are adding a cusp in it. That one just tells exactly to your system, hey, when you get too close, just go away. And we are optimizing it at the VNC level. So basically what happens, and this is here, I'm plotting just the two-body JASTROW function with the distance here in bigger size. So this is just a representation of how it's behaving. We see here, if I just take one determinant, so my JASTROW function is doing a lot of work. Now I increase the number of determinants, and basically I'm just removing more work from it. So basically you have this competition between the JASTROWs that I'm having and the multi-determinants which are already there. So this is why at QMC level I can increase the energy faster, because basically the moment I am correcting for the nodal surface away from the cusp, the rest part is already managed here. So how?
I think it's also worth noticing, right? Even with 1 million determinants,
Yes.
close in, right? The JASTROW is still doing a huge amount.
Yes. Exactly. This is a very important point because basically what's happening is that I am still truncating my wave function. The space has 10 to the power 36, and I'm just taking 1 million. So there is still a bunch of determinants that I'm not getting. So the JASTROW here is just fixing everything that I am not putting in there. The JASTROW is correcting it, it's cleaning it. The JASTROW is your friend. I should have a t-shirt and offer it to Michelle. So, and how to demonstrate this? Even further? I'm gonna come back now that I explained this. Sorry. We tried a little experiment. So we have a very good optimizer in QMC pack, and I think Pruning is going to talk even more, and this is done with the previous version. So we know that now probably the optimizer is going to be able to do more things. So what we did is I took my system with 8 determinants, and I tried to re-optimize the JASTROW parameters and the coefficients of the CIs. So I just said, here's 8 determinants, 226 and 2000. They all have this weight. However, I have JASTROWs that are pushing for this. So maybe with my JASTROWs, the weights of these determinants are going to be slightly better or slightly worse. The important ones in presence of JASTROWs, if there is one that is there and the JASTROW is doing exactly the same, might drop. However, the ones that are needed for long-range correlation that are struggling too much might just be promoted. So we did this, and you see here, it's the plane curve. That actually I am gaining significantly more energy by doing this. Here with 2,000 determinants, I am actually converged compared to the 1.2 million determinants, or even to the 160,000 determinants. And this is a fantastic news for us. So this is great. That means that even with a smaller number of determinants in presence of the JASTROWs, you can have a good numbers. So which means for large systems, since the method scales factorially with the number of determinants. Yes, sir.
Is everything being optimized, or just this
No.
CSF coefficient?
So this was optimized, everything optimized at the same time. However, we know that, yes, Paul?
But I think the molecular orbitals are not
Yes,
being reoptimized.
yes,
So
sorry.
this is the determinant expansion and
Yes.
the JASTROW, I think.
Exactly, sorry. This is JASTROWs and CIs, because there's also the option of optimizing JASTROWs, CIs, and also the orbitals at the same time, which would give you even a better or less number of determinants. I think the count from Cyrus did some trials like this, and when I need about 3,000 determinants, he needed about 300 determinants. Of course, for large systems, you cannot afford to do this type of things, and this is the point where I was going, is that unfortunately at this point, we cannot do large system optimization, and about 2,000 determinants in the CI is the limit that we can reach. You may think that 2,000 is already large, but for larger systems, remember, the method scales exponentially or factorially with the number of orbitals that you have. So if you needed for a small system 2,000 or 1 million determinants to converge, well, if you double the size of that system, I'll let you do the math, but technically it's going to grow factorially with the number of orbitals that you have in your system. So the method is still very expensive. The goal here, the key, is that because we are using QMC with JASTROWs, and we have this stochastic method that is extremely powerful, even for large systems when we cannot converge the energies at the selected CI level, QMC is there to complete. Again, we have the JASTROWs that are there just to complete your space. So this is the goal. Another thing that is worthy to notice is that this attempt to optimize the CIs was our first attempt to do this type of things, because not many people use this for QMC, and we're the only ones who use JASTROW with it. So there are multiple ideas that we started scanning on how to really optimize efficiently. Should we fix the JASTROWs and optimize the CIs instead of optimizing everything together? Should we do one after the other? There are other ways, and basically, if you're interested, there's a lot of things that we can just, like, here's an easy thing that one can do, etc. So this is quite an interesting project. It works for solids. It works for molecular systems, and hands-on that I'm gonna, so these are the results for the solids, and I'm just gonna show you how to run this with, for a molecule system that is quite easy to do on the Amazon workstations. Okay, so I selected H2O because yesterday in the talk about molecules, I showed water examples. So that would be nice to just complete this so you can see the difference between using water with multiple trial wave function we did yesterday. I showed the results for PDE, PDE0, and DETERMINANT, of course, HARTREE FOCK. And now we're going to complete those results with selected CI. All the examples are available on the workstation. And actually, the code is called also quantum package. So we're just happy because the second paper for version 2 just got accepted, I think, yesterday or the day before. So we're pretty happy about it. Yes, so this code is available. It's an open source code. You can download it on GitHub. They have a GitHub support that they can answer. They simplified a lot the installation of the code. It used to be a nightmare. Now it's not as much of a nightmare. It's just usually a panic attack, and then you wake up and you're fine. And basically, it's so if you pass the point of the installation of the code, it becomes a very, very nice and easy. I'm not going to sell you.
I would just say the new version, which we put for the Amazon Web images, we actually found it to be pretty straightforward because it can install the dependencies now,
yeah.
Whereas before that was extremely painful. So it's much improved in my opinion.
So maybe if I can, so basically they use their own. They try to oversmart the system, so they wrote their own programming language that generates extremely efficient code. So yes, it makes code that is extremely efficient. Even Intel uses their code to generate codes to test their new compilers, but it means that you cannot read it. It's a language called OCaml, only used by, I think, 3 labs in France. It's fantastic to contribute to this code. I think Kevin here can tell you nightmares that he had to try to add something. So anyways, but the moment you use it, it becomes very, very easy. So the code, because they made it even harder, they have their own visualization and their own editor. So, yeah. So it takes only one input file. The input file, that's the only thing that you need. You just need an XYZ file that is completely standard, like you can see here. Every time you want to use, and this is important because if you try the code, it's so simple to use and so easy that probably you should just try just for the fun of it, but you will fail at the first step if you do not source the source files for the code. So it just requires to source it. The moment you source quantumpackage.rc, you're good to go. So how you create a file is pretty simple. Everything goes with command lines. You can just type qp create. You specify the basis set, -b. If you do not know which basis set to use, you can just do -b show, and it's going to show you all the list of basis set available. It's very intuitive. You just do qp create, and it's going to just give you all the list of things that you can try, and it works pretty well. You specify the basis set. Here I am adding a basis set at triple zeta with core, so we can excite from the core electrons, because for the case of H2O, this is something important. Hydrogen does not have that. This is why I'm specifying them separately. And I give this. So from here, it's already gone. It's done. qprun now is the command, quantum package run is the command to be able to run the method that you want. And quantum package has multiple methods available. So you can run single CIS, so this is for single excitations. So you can just do the single excitation, it's going to give you all the single excitations. CISD singles and doubles. You can decide to rediagonalize your Hamiltonian if you want, because why not? You have full CI. You can call full CI dump, which Miguel talked about yesterday, because this is the format that can be transferred from one method to the other. You can do consham SCF. You can do range-separated DFT, where you put a DFT at the short range, and you can put HARTREE FOCK on the long range, so you can do multi-reference on the long range, while you kill this problem that I was talking about of the cost at short range. You can just replace that by a DFT potential, and that works extremely well. We're writing a paper on that, and it reduces significantly the number of determinants you have. You can see here that is a special tag for QNCPAC, so it's fully integrated with QNCPAC. Once you click on, you call say for QNCPAC, you'll be able to generate input files for QNCPAC. It's a pretty nice type of system. Okay, I'm not showing here the editor, and maybe I should have just demonstrated quickly the editor. But basically, qp edit, so it is on the README file that I give you, and I encourage you to try it. QP-edit will generate a classic type of input file that you can see, that you can go through to see all the parameters that you have. So if you just enter QP-edit and the input file that you have generated, it will allow you to really go and see what you have, like the basis set that you chose, the coordinates, the geometry, if you want to save the wave function or not when you do calculations. They have their editor, so it's their own editor that they made. And basically the reason for that is that it's foolproof. So it's stupid proof or Anouar proof. So basically I can enter anything that is not physical or does not make sense. The editor will not accept it. And it will just say, no, you don't know what you're doing. Do not put this. Before even I run or it fails and it crashes for some reason. So it's pretty nice for this, and it complains whenever you try to put something that should not be there. If you're trying to put like a negative number when it does not make it, it will just complain about it until you go home, you're drunk. So, okay. So now we're gonna run to begin with. Again, I'm just going through these examples, and the ideal would be to really try them again. So I'm just going to go through the basic things and tell you how to analyze the data that comes out of it. So first, when you start, if you remember step 1, we said you need to run your ground state, your HARTREE FOCK, and this is what we do here. So to call HARTREE FOCK is just SCF, so you just type qp run SCF. This is your input file, H2O, EasyFIO. This is the file system that they use. So your function is your system is going to be named like this. And I just direct it to an output file. And this is the typical HARTREE FOCK energy of water that you find using any code like BySCF or NWChem. And this is for a triple zeta. Now, remember, quantum package, the point of doing selected CI is to have the most compact trial wave function you can get. So your point is to be able to reduce the number of determinants that you are using, or at least for the same number of determinants that you decide, having the best quality nodal surface that you can. So one thing that you try to do is to just have a good start. Remember, when we try to do these excitations, if you have the wrong HARTREE FOCK, all the beginning of the excitations that you're going to start with are just going to be to try to correct for a bad HARTREE FOCK. So one way to reduce the number of determinants that you use is just to have a better starting point. So here I choose natural orbitals from HARTREE FOCK, but in a paper that we are writing with a bunch of people here, we even start from B3 orbitals because they are way better, and it doesn't matter. It's just basically as long as you have, you're going to the Hilbert space, so you don't care. You can just add as many as you want, as long as you have a good starting point. So,
Anouar, is the code checking whether they are orthogonal or not?
Yes.
Now imagine the revolutionary idea. I would just pile in infinite garbage of orbitals.
Yes.
They won't be orthogonal or nothing. What would the code do?
In this case, it's not gonna like it because it's gonna try to orthogonalize.
Try to orthogonalize.
Yeah, but if we remove the orthogonalization, I don't know I think it might just go everywhere.
It's a good idea. It's what's right. It's a good idea.
I think
because Miguel mentioned it.
Yes.
If you just go into non-orthogonal, you by definition decrease the whole thing by order of magnitude or 2 orders of magnitude.
And the count, even so we spend more computational time just orthogonalizing the determinant in the selection process. So if we remove that, I do not know what we might find, the quality that we might find, but it might reduce even the cost of the computation. And that's probably...
There will be something, to discuss with Michel, because imagine that you say all the codes, of course, rely on the fact that it's orthogonalized, which is increasing cost and decreasing the efficiency, actually.
It is.
And if the code will be so robust that it will tell you, I don't care, I just need to, the whole thing would be much longer, but you gain 2 orders of magnitude on expansion. So suddenly there might be a...
I think so. We had mentioned this in the past, and basically the answer was, please send us people, give us postdocs, sit with us, or it's not a no-based... No, but I have more... I built it to be able to be current discussion, and so that's the but yes, that actually would be a great idea. Yeah. So, so natural orbitals. So again, starting from natural orbitals is a fantastic thing. One way to do it, and maybe I should have mentioned this. So, what is the criteria of exit? So when does the code decide, okay, I'm done, I'm gonna exit? So you can just select the threshold that you want to achieve. So if you say, for example, I want my energy to stop, once I add determinants, I want my energy to stop improving beyond 1 milliHARTREE, or 10 milliHARTREE, or 100 milliHARTREE. Or you can just say, you know what, I don't care, I just want a maximum of 1 million determinants, or 100,000 determinants, and I exit. So this is here what we do. I can just put 50,000 determinants, and I just decide, you know what, this is a quick run. I just want 50,000 determinants just to build the natural orbitals because it's not that simple. So it sounds, by the way, 50,000 determinants sounds a lot. This takes about less than 3 minutes on your laptop for the H2O for this system. So this is rather, it's just like push it and it's going to converge right away. The reason for that is that the code is extremely parallel for this, and even on one node, it's just, this is nothing. So here you see that because you cannot force, when you do the selection process, it cannot just say I'm going to take 50,000. It's just going to select all the ones that enter. If it's above a little bit threshold that you put, it's just going to exit. This is why here you get 63,000, because at the step before you were under, then it selected all the single and doubles, but it entered more than needed. And when they fit the criterion, they're already computed, they stay. So you can see here, the way to run this is just you do QP run, FCI for full CI, even though technically it's not a full CI calculation, it's selected CI, but whatever, and you just run it. When you run this exercise on the machines, you're gonna see that you're gonna see the iterations, and you're gonna see at each step how many determinants are there and everything. So you're gonna be able to track it and to follow it, and it's extremely nice to see because it gives you the satisfaction to see how good you are going. And this is the last step here. So if you remember, we started from this energy. Now with 50,000 determinants, we added 0.32 HARTREEs to the energy. That's huge. Now it gives you here the PT2 value. So we know that we are introducing still, we are probably around 0.014 from the full CI energy. So we know that if the accuracy that you wanted was the milliHARTREE, well, you're still far away from that. However, when you do the energy, you get this 389, which is very close to the full CI energy at a triple zeta, by the way. So there is also a new tool that was added, which is print energy convergence. If you just type this command, qp print, it's just going to give you all the cycles. So at each step, the number of determinants that were introduced, your energy and your energy plus PT2, and you can just plot it. And you can see the shape that it does here. So this curve here for H2O is quite interesting, and I wanted to just like stop 5 seconds to help you analyze when you have results like this. So first of all, you see here, this is the error that you're introducing, by the way. This is the energy plus PT2, and you can see that at first the evaluation is pretty poor, but very quickly it's almost flat all the time. So you know that there's nothing much is going to move here. You already converged around 1,000 determinants for H2O, which is good because technically H2O is a closed shell system. There's no reason for it to be more complex than that. So you do not need to have multi-determinant. There is no reason. The truth is more that, well, the basis set is the problem for systems like H2O, and you need basically the multi-determinant is correcting for the basis set, not for correlation that you're missing or some weird thing that should be happening. The second thing is what happens here around 12 determinants. You see here a drop in the energy. This means that the HARTREE FOCK that you have started with, or the ground state that we started from, was not really the best to begin with. So you start adding determinants, and at the second step, the system just says, oh, I needed these determinants. They are really important, and once you add them to your count, it just drops the energy by this sharp drop from one set to the other. This shows that your HARTREE FOCK was not really nice, or your ground state could have been slightly better. And this happens quite often when you start with HARTREE FOCK, because there is no method that guarantees you to find the ground state of a system accurately, and this is why if you can guarantee finding a good ground state, you won't have these things. So, okay, now that we have about 50,000 determinants to begin with, you can just rotate them and generate the natural orbitals from them. And this is an operation that takes about a second. And you just do QP run, save natural orbitals. And now you can start again with 100,000 determinants. So it's kind of a little bit ridiculous what I just did here, because the previous round I had 50,000, now I'm just doing 100,000. But I wanted to keep the example less than 5 minutes on the workstations, so you can just run them. So again, 50,000 was not really the best that I could do, because here you can see that I'm still getting this sharp thing here, meaning that I'm still not entering my ground state is still not very nice. But what you can do is you can repeat this operation multiple times. So there is no reason for you. You can do HARTREE FOCK, then you do 50,000 determinants, you save the natural orbitals, and you do another 50,000, and you just do this. A few rounds would have smoothened this, but I just wanted to do it just once, so you can repeat exactly the same thing. Sometimes, and this is the key, sometimes it's not enough to do this. So one thing that you can do, especially for transition metal oxides, what you can do is do all the single excitations, and you enter them in your system. You force them to stay there, and you do the full CI with all the singles there. So what happens is that sometimes those singles might seem that they have a very low energy, but then if they are not there at the beginning, when you start exciting, you miss that excitation that can come from one single excitation. So there are a few tricks, and if you decide really that this is what you want to do, don't hesitate to send a mail to me, to Ken Jordan, to Bosch. These people are quite experts in chemistry. Me, I just run 10,000 times natural orbitals until I get all of them. And this is why it's foolproof, and the fool is me. So, okay. So you can see here that at the end when we run, so now I'm using 100,000 determinants. So my energy now is 37. I cannot move. Okay. So the previous round.
Which one do you want?
Where am I? Okay, here. That's good. So you see here, I was 374. Now, just by adding one round, why is this not doing what I want to? Okay. So I was 374. Now I'm 377, and this is just one round more. So just adding a few 50,000 determinants, so doubling, going from 60,000 to 100,000. I already gained about 3 milliHARTREE. Know that when you converge, these two curves here should touch. That means that the evaluation, the exact evaluation of your energy and the estimate error that you are having should be the same. So we know that we need to converge to this value. And the difference here tells you how far you are from that effective convergence of your energy. So now the question is, do we get, oh, sorry.
Have you seen such cases where the PT2 will show you that your energy is pretty much converged, but DMC has lots of way to go for the conversion nodal surface?
Yeah, it's in the two slides, yes. It happens in the sense that this is basically, there is no paper to back what I said about PT2 converge means nodal surface converge. This is a feeling based on the previous cases that we tried, but ideally we would need still to do some work here, because the point is that we are optimizing JASTROws at the same time. I think this is more a question of we need to put a protocol in place to how to deal with these wave functions, and that was not done yet. For now, we are still exploring how to use these things. Because again, the way that we do it, I take this 1,000, I fix the coefficients, and I try to optimize JASTROws. This is what we do, which is stupid, because JASTROws are flexible, the multi-determinants are not. So I should probably fix, or JASTROws are cheap, multi-determinants are expensive. I should fix JASTROws and optimize smaller number of coefficients. There is something to be tried on multiple levels, and the problem is it just takes time, and we need more hands, and we need more people to be interested in this, to try this. But there is the protocol that I've been following so far is not the most optimal one. I have some ideas, but if anyone has suggestions, that would be a great conversation. Okay, so truncating the wave function. Again, if you remember, I said that QMC does not need as many determinants that we need in the expansion of the multi-determinant. So one way to do that is just to remove a little bit of the determinants. If you remember earlier, I showed you I used at the DMC level 8 determinants, 100, 200. So how do you cut these determinants? You can by just saying, okay, so the coefficients of the determinants that I have, if they are higher than X, remove them. If they are lower, keep them. But when you have your matrix representing your determinants, you're just going to end up with a sparse matrix. So it is, I think, important to know that when we do an evaluation at the DMC level of a multi-determinant, of a determinants, you have the part that is alpha and the part that is beta. So in order to build determinants, you just need to do the unique alphas and the unique betas. If you have a determinant that needs an alpha and a beta, if that alpha was computed from somewhere else and that beta from somewhere else, that new determinant that you have is for free. So basically what it means is that you only need to evaluate all the unique alpha excitations and all the unique beta excitations. And any determinant that is built with one of these will be free. You won't have to pay for it. So if you arrive and you just decide, I'm going to remove all the determinants that are lower than some threshold, you might be removing a determinant that is going to be used for a lot of them. And you create a sparse matrix like this. So yes, you're going to have less determinants, but the cost in evaluation is going to be higher because now you have removed one that was used by others. However, what you can do is change your truncation criterion. So you just do it on the norm of the coefficients. If you do this, you're basically only removing determinants that are not using any construction. This creates a more dense matrix by part, and then you're going to have more determinants in your expansion, but at a lower cost. And we can see it here when we use this thing here. So this is the product here, and this is the number of determinants that you have. So we're basically able to get the same accuracy or even more with less number of determinants that we are using compared to just doing this. So this is what we do in quantum package. And basically, we do it for 4 truncation points. So we just want 4 points to be able to see how the evolution goes. So you can put it, for example, in a loop. And there is a command for that, and that command is truncate wave function by spin. So you just copy, and this is an important point today, where if you try this, if you truncate your wave function, the determinants that you have removed are gone. So make sure that you make copies of your directories. Otherwise, you will have done 1 million determinants and you just truncate it, and now you have 200 that are sitting there and you cannot do the rest. So just make sure that you work on that. This is why it sounds stupid, but yeah, just do this, it's going to be fine. So when you do this and you do this truncation 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, 10 to the minus 8, it corresponds to 2,000 determinants, 18,000 determinants, 44, and 98,000. You see that the energies, as we were expecting, go lower with the number of determinants, which is normal. You wanted this. But at the same time, you look at here, the energy of the energy plus PT2, it's more or less the same to, so here we are accurate at the milli-HARTREE. Starting here, we are almost accurate all the way through. So it does not move that much. So we know that we are almost there. Okay, now we save for QMC pack. That's the last step. QMC quantum package has internally a saving for QMC pack. You just save it, and now we call the convert for QMC like we did yesterday for the molecules, except that we put QP. So this is a note. Quantum package also writes natively an HDF5 file that can be read automatically. But I just prefer to use this one for here, so you have an idea on what's going on. But you can use either one. So it's when you run save for QMC pack, it will also generate a file called qmc.hf. That H5 that you can use exactly like PySCF, and it works directly. So convert for QMC-QP, production, and you remember I'm not going to go through these tags again, production and add cost because we are doing all electron calculation. And maybe just here take 5-second pause. So it also works with pseudo-potentials with the NCSU by adding just -P NCSU, at least it should work, or the BFD. So they are all, both of them are native to QMC pack. Now, the trial wave function. Once you run this and you do the conversion, there's a new tag that appears in the trial wave function, and this is what I'm showing here. So this is the input file for QMC pack. This is the WFG file, FJ file. And basically what you see is this multi-determinant line that is different. So you see here, this is for the truncation at 10 to the minus 4, where we have now a determinant list that has 2,600 orbitals, determinants, the number of electrons that you have, and the number of states, or this is the number of orbitals that you have in an H2O system. You have 71. Cutoff. So you can also, even if we have truncated inside quantum package the orbitals, you can also add an extra truncation inside QMC pack. And you can just say, well, if the coefficient, the size of the coefficient is smaller than 10 to the minus, you can change that to whatever you want. Don't use them. I don't recommend this for the reasons that I showed earlier, which means that you might be removing determinants that are necessary. If you want to do a truncation, I would really advise to do the truncation inside quantum package, so you have a very compact type of matrix, instead of doing it inside QMC pack. But sometimes I'm lazy and I have computer time. I just put there and I just say, that's fine. So don't be lazy. Don't be like me. So, okay, so we have this. So, if you were a QMC pack user in the past, you might not recognize this format. It's just because we have 2,000 determinants here, but sometimes in larger systems, I may work with 3 to 4 million determinants in my QMC. And if I have an XML file, if we were to just state them all in an XML file, it used to take sometimes up to 20 minutes for the system just to go through the files, which is completely stupid. So now I moved everything to HDF5 file. So now it takes about a few seconds to read any size of the system. So you don't have a description of what is a multi-determinant. But if you do not use the tag that I just put earlier, you actually can get a wave function that looks a little bit like this, and this is the old format. It's still red, but this is nice to visualize. Unfortunately, there is no better way that I have thought of, or we thought of, to be able to show what is a determinant correctly. But this is something that we're trying to figure out how to represent, how to visualize what is a determinant. And that would be a good tool visually. So far, we just have this. It's still good. So coefficient 0 is the ground state. This is your HARTREE FOCK determinant. As you can see here, you have the alpha and the beta. This is the 71 states that you have. You have electrons on the first 5 for the alpha and electrons on the first 5 on the beta. And you have the weight of this coefficient is 0.97. So all the weight is located on the first determinant. And this is what you're supposed to find for a closed shell system. However, you still have 0.03 that is split amongst all the others. You see coefficient 1 here. So this is the first excited state. You have, strangely enough, the most heavy one is not the one that is just one single excitation. This one here is 1, 2, 3, 4, 5, 6, 7th excited state is the one that is better. This is probably coming from a really, really bad trial wave function, the starting point that we have started with, because having a 7th excitation as the first one is basically a good sign that something weird is going on in your system. You remember that jump that we have? So because we do singles and doubles at the first time, then we did singles and doubles. So it took a little while before we entered the 7th excitation here. And this is why we see that gap, that jump that was back here, and this excitation here happens. And now we're starting seeing like the other ones that are the normal ones that we're expecting to do. So I just got it at 5, but you can plot this, you can print this, and if you think of a way to be able to represent this in a better way that people can, please let us know. That would be a great idea. Okay.
What's the difference between the two different coefficients?
So this is a legacy.
QC.
Yeah, so this is a legacy from Miguel. Wanted, in case you were to optimize the coefficients here, in case you only optimize this part and this one stays fixed, so you can compare the old and the new one. But I think he also, at the beginning, he was trying to play some tricks on the coefficients to be able to use 2 different types of coefficients on them. But this is why this is now it's all in HDF5 format, and we don't store the second one. It's basically just this one. This is just old legacy. I really don't recommend, unless for visualization, I don't recommend using XML for this because it's really heavy and it's not really useful. Okay. Now we optimize the JASTROWs, just like for the H2O systems yesterday. We have showed 2 optimizations, one for the 1 and 2 body JASTROWs, and another step for the 3 body JASTROWs. This weird point here is a VNC point, a starting point, so it just started weird. I don't know why, to be honest. It's just a weird point it started with. But the energy just changes a little bit compared when you add 3 body JASTROWs. However, the variance, you see a net benefit by using 3 body JASTROWs. So this is something that I noticed in using multi-reference. 3 body JASTROW is the most important friend you will have because it reduces the variance by almost a factor 3, which means that you are making a speed up at least of a factor 9 in your cost, knowing that the cost of a multi-determinant calculation, the more you add determinants, so if you have two determinants, technically the cost is double, because you do the evaluation for one determinant and the evaluation for two determinants. So when you have 1 million determinant, your cost should be 1 million times more expensive. If you can reduce by a factor 9 your cost, that's a good thing. The reality, because of the table method, because what I told you that we only evaluate the unique alpha and the unique beta, actually the scaling of the cost is not linear with the number of determinants, but more closer to square root of the number of determinants that you have. And because you have also gains in the quality of the nodal surface, which means that your variance is lower, you also have to divide by whatever benefit you have from the variance. So it is not clear, but it's definitely lower than that. Otherwise, we won't be able to do anything. Now, for these truncations, I can plot the energies now at the DMC level in function of the number of determinants in a log scale. So we see that this is the energy that I have here, 76,423. And at the QMC level, at the largest truncation, I gain not that much. However, so I added a point from a previous calculation that I have done that you don't have in your system, which I just put 2 million determinants, and I run them at the QMC level, and you're around 31. So it's 76431 here. So that's with the number of determinants, and you can see that it's very difficult to estimate how much we can do it. However, if you plot with the value of PT2, and this is what we do in the publications, so PT2, if you remember, is the error that we're introducing to the full CI limit. If we were to do a calculation on top of that, we would also have the correct PMC. So basically, so I did not, I'm sorry, I apologize, I did not do the fit here because it did not work quite well. But in fact, because my error bars were large, these are results directly from the workstation. If I had done them a little bit more seriously with slightly more nodes or longer, I would be able to get a better fit for these energies. But basically, you can use a quadratic fit here, and you can extrapolate to the 0. So what you want is the energy at 0, and this is what we use in general. So even without this, you can see that we're not very far from 0 here. This point here is at 10 to the minus 2. And basically, we're still far. This is not a finished story in the sense that if I use all this and I get the best result for double zeta, triple zeta, quadruple zeta. So this is what I showed you yesterday. This is what you have in your files. You can generate these data points. These are all the single determinants. And this is the selected CI curve that I have. So you can see that actually, no matter what, I am improving systematically my wave function. It's smooth at the level of the DMC. I can get, the error bars are here. I can get really this curve to converge. And this was done by actually Kappa and all in 2016. This was their big paper on water, where this curve here is DMC values at different basis sets. They added one point at the 5Z that I don't care about. The space, as I said here, so for the double zeta, it's 10 to the power 10. They used 100,000 determinants. And for the 5Z, it's 10 to the power 19, and they used a million determinant, and you can get all these points, and you can extrapolate. So the experimental value, this comes from some experiments with non-relativistic effect and 0 point everything, is 764389. The QMC energy that they have is 43894. So they are even more accurate than the experimental measurements without having to go all the way to the full CI by just having this. So all this you can do with the tools that are installed. And it's possible to, I hope that I demonstrated that it was possible to systematically improve your nodal surface to the point that you can get the exact energy and remove all the nodal surface error. This works for solids, it's slightly more tricky. This is still a very, very research topic. Molecules is slightly easier because you don't have to do all the finite size corrections that come with the solids. The max size, do not attempt to go beyond 350 orbitals for molecules. Solids is slightly different system, but I don't recommend you trying this on solid yet. It's research in progress, so if anyone is interested, have questions, please don't hesitate. Thanks.
Thanks so much, Anouar.
Just one comment. You didn't mention the most valuable feature of this method. You know what it is? I mean, besides getting nice nodal surfaces and all that stuff, you get also part of the spectrum.
Yes. Yes, so I did not talk about having excited states or doing.
That's
Yes.
the hard part. You know, in QNC, we can't just push the button and get another state or something like this. While from that stuff, you just spit out the first 20 states.
Yes. So basically, one of the biggest, that you're completely right. So let's say, for example, the molecular systems, when you do the excitations at each step, you can also, if you diagonalize and have only the first eigenvalue, that's your ground state. But you can also diagonalize and have the first two, and that's going to give you access automatically for about 20% of the cost. You're going to have the first, the ground state and the first excited state. And you can do even the selection of all these in parallel. So you gain a huge amount of time, and you can have the homo lumo for free. So you just run it and you have it. In the solids case, you have your band gap. If it's direct band gap, you have it for free. So this is the first application that is pretty nice to do. And we did a few papers on the excited states like this were just, oh, so it's so free that we should just do it technically all the time.
So I didn't understand it. Does this work for solids?
Yeah. So the
Okay,
first.
I thought you just said don't use it for solids.
No, I just said it's a complicated task for solid in the sense that we're just writing the paper with Paul, Ken. So we just implemented everything now that we can do extrapolations. I gave a few talks about it now, and we are writing the paper about it. So it's the only reason why I say don't try it for solids at this point is one, the cost. And two, we have not written how, I did not show anyone how to use it, so I think I'm the only one who can use it.
No, but for solids, I mean, you just have vertical excitation, or
Technically not. I can have any K point. I can excite from different K points. It's just, so Jaren is building up the tools, because the problem is that it does not, no tool is designed to use this. I don't think that people expect, so we have Nexus, that generates all the tricks to be able to do things. So for example, quantum package does not manage periodic boundary conditions. So we have to go from PySCF, generate everything, but PySCF does not generate symmetries correctly. So we have Nexus generating the symmetries that we need, giving them to PySCF, recovering them from there, doing a transformation in other machine, then putting them back to Nexus, to currency back. It is.
I'm still, okay, so in the molecule case, I mean, with a finite basis, there's a finite number of excitations.
Mm-hmm. Yes.
But in the solid, even with the finite basis, there's an infinite number of excitations.
It depends on your band.
No, I mean, because you can have, 3K point, 2K points, 3K points, whatever, you can have 5. I mean, you can.
Yeah, as long as the excitation is within
but the K
points.
spectrum is infinite. I mean, it's continuous. So.
In every code, you use K-mesh.
Yeah.
It's exactly like the basis set in, in real
Okay,
space. It's a
fine,
basis set.
but for the molecule, it's an exhaustive for a given basis set.
So for a
It's
solid, you
exhaustive.
have an additional convergence parameter, which is a K-mesh.
Right.
Right. But of course, you have to define a discrete K-mesh in order to do the
Yeah,
calculation.
so you have a
And there's
K-mesh,
actually,
so
because of the symmetry, there's a lot of
additional
juggling.
multiplication by another basis. So it's just a larger basis.
Yeah, but okay, even for your K-mesh,
So
you have every possible combination.
We converge all of them. It's
So-
convergent.
No, but it's an infinite set, even for finite K-mesh. Yeah.
Well, I mean, it's infinite for the molecule too, but you're right. As you go to formally converge the solid, you have to go to larger and larger K-meshes.
No, but even for a
larger and
given
larger
K-mesh, I mean, you have every possible permutation of those K vectors. That's an infinite set.
if K,
Well, there's
number
a
of K points is
K
finite,
points and a finite number of excitations around it, so it's large very quickly.
It's
not
because
large,
large,
but
Infinite
there is-
set.
there's nothing.
It's an infinite set.
Once you put the mesh, which is a finite number of points, all the permutations might be large, but they're
Yeah.
finite.
No, they're infinite because there's any number of those. Let's say you have 4 K points, so you can choose not just any set of 4, but you can choose any set of those in any order up to infinity.
Of course, but you have special K points that you select. In the,
No, I'm saying of those special K points.
I think this is a good topic
Yeah,
for the
okay,
break
okay,
when we get
okay.
to it.
Okay.
We'll see how we can generate infinities from a finite set. Any other questions? At the back, and
Just a comment. You talked about ways of truncating the space.
Yeah.
One way that I know that you use frequently is to use the natural orbitals and to put a threshold on which natural orbitals to keep.
So I think if I heard well, so Ken said we can truncate the space, and one way to do it is to take the natural orbitals and put a threshold on the number of orbitals that we add in
on the occupation number.
Yeah, yes.
And if you do that, when you showed the result for water and you had this funny excitation,
yes,
that might go away if this calculation was done using the natural orbitals.
Yes, if that's exactly the case. So if we truncate the space and we just like force that we might not get that seventh excitation, that is just going to be weird, then we can get a better set of natural orbitals out of it.
And the other thing I wanted to comment on, and maybe this is too much of a detour, you presented the quantum package as though everything is deterministic. There's stochastic steps in there too, in the configuration.
I did not. Ken says that I presented quantum package as being deterministic, but there is stochastic parts in it, and that's completely true. So basically the selection process, because I did not want to go too deep in the details about quantum package, but in the selection process, when it started, it's deterministic, but now we have changed that and it's not deterministic anymore at the beginning. So you have stochastic, a semi-stochastic evaluation of the determinants, because we know that, for example, at the beginning, most of the single and double are going to enter. So there is no need to evaluate the error that you're introducing in them at the beginning. So you just do enter X amount at the beginning, so you speed up your calculations, and then you do an stochastic evaluation by sampling through your determinant space to be able to evaluate that error. So this is why I present all the errors on PT2 with an error bar on them. But that error decays quite quickly. So it's a semi-stochastic method, but it does not matter too much. It's just speed up the entire process.
So if you apply this to binding reactions, would you get, would this method show any size consistency issues?
It is not size consistent.
Okay.
So the method is not size consistent. So, however, one way to do it is, if you're converged, if you can guarantee that both your fragments and your solid are completely converged, then you're fine. And we did this for smaller systems. Otherwise, one way to do it is, you do your molecule, and then you separate your molecule by 10 angstrom, and you redo your calculation of it, and then you ensure that you have size consistent. It's just slightly more expensive, but what's a few million core hours between friends?
all right, thanks very much, Anouar.